This is Lab Report 4 by Jack Palacio. For an introduction to this experiment, the purpose is to examine the motion of a spring mass system while it swings in an arc and is oscillating on the spring at the same time. Then we will observe how the predicted and observed motion differ from one another. The system is the mass, spring, and earth, and the surroundings is everything else that interacts with it. The models and principles we use are Newton's second law and the energy principle. And then a brief overview is the total energy from beginning to end stayed the same, proving the conservation of energy theorem. So the equations we use is the first one is kinetic energy, which is just 1/2 mv squared. This is potential energy for gravity, which is just mgy. And then spring potential energy is just 1/2 ks squared, with s being L minus L naught. And then k is equal to the constant, and we'll be able to find that, the oscillation period, and just plug it in to this equation. And this is the spring force, which is just negative Ks times L hat. So for the system properties and initial conditions, the mass of the ball was given was 0.402. These are just the position of the ball relative to where I put the axis. Just found that. And then that's it for the initial conditions. For the constants, we have G, which is just 9.8, gravity. Ks, which is the spring constant, 6.83. And then we have L naught, which was just analyzed from the video. L is equal to the ball position minus the spring position. And then S is just equal to L minus L naught, like I said earlier. This is just using the equations that was on the last slide, just putting them all in here. So we have kinetic energy, which is 1/2 mv squared. Gravitational potential energy, mgy. Spring potential energy, 1/2 ks s squared, and then just adding them all up. So here's the calculation loop. We define all the initial energies, and then we're calculating the gravitational force, which is just negative mg. The spring force equals negative ks times s times L hat, and F net is just both of those forces combined. Here we're putting it using Newton's second law to apply the momentum principle. This is just the velocity and position update formula. And then this is L hat, and S. And then here we're calculating energy changes. So it's just kinetic energy, potential gravitational energy, and spring potential energy, and then we're just finding the change by doing delta. So here are the results. The exposition for this is time. It starts off pretty similar. However, as time goes on, it becomes more and more differentiated. Same with y position in time. The model is a lot higher than the experiment. This is likely due to sources of error. Um, the experiment's not an isolated system, so there's other forces at work, like air resistance. There's also human error, not clicking in the center of mass every single time in Tracker. It's pretty difficult to do that. So what does it mean? As you can see from the graph right here, the energy principle is satisfied because the total energy remains constant throughout the whole experiment. This orange line, which is the change in energy, it does not increase or decrease. And then for the oscillation periods, we found it's 1.637 seconds, and the y direction is 1.592 seconds, with a difference of 0.045 seconds. Like I said earlier, this is likely due to other forces being at work.